Okay, so we'll continue on Laplace transform properties. So today is Monday the 19th. So what we did is exam 1 intern, and we will discuss Laplace properties, which is the readings from page 58 to 95. Then in Wednesday lecture, the readings between 95 to 98. Then in lecture, on Friday lecture, is the due date for homework 6, and the readings are page 98 to 99. Homework 6 as well. So please make sure to go to Canvas and see homework 6 start answering them. I encourage you to start after today's lecture. Okay? Now, last lecture, I mentioned about the poles and zeros. So basically, poles are the roots of numerator, zeros. So we have, x of s equals numerator over denominator. So poles or zeros are roots for numerator, while roots of denominator are poles. So depending if you are working on poles or zeros, so zeros in the plot will be written by O, while poles in the plot will be written by X. Okay? So basically, poles are related to the value that make the transfer function as infinity, or the function as infinity, while zeros, that makes the function as 0. Okay, that's why they're called zeros. Now, here's an example. Find poles and zeros for this function. F of s equal to s minus 1 over s squared plus 1. Now to find this, zeros, the roots of the numerator, so which is s minus 1 equals 0, therefore s equal 1. Poles, the roots of denominators, which is s squared plus 1 equals 0, therefore s squared equals negative 1, then the square root of negative 1, which is I, or we call it j, the imaginary number, so it will be plus minus j. Then if we need to plot this in the xy or real plane mode or xy plane mode, this is the real number of s, here's the imaginary number of s, then we will say the poles at negative 1, so it's s equal 1. Here is 1. This is the pole, while the zeros are at positive j and negative j. Then that's it. This is also how we plot them. So you need to know how to plot them and how to find them. Finding the roots is easy, and also plotting them all is good. Just keep in mind that we will have a complex numbers. We can have some complex numbers. It's possible. There's no problem. Okay. Let's go to the continuous of properties in Laplace transformation. Well, again, we can see that tables 3.1 and table 3.2. So we will try to discuss these properties. We already discussed the linearity. Now let's go to time shift and go for some frequency shift as well, and some other properties. So you should know table 3.1, 3.2 in the textbook. Those are very important, and you should be aware of all of this. Let's go to notes. Let's discuss time shift property. So here, basically, if the system is causal, if x of t is causal, and that's most likely all of the real life systems are causal, which is x of t equal x of t, u of t. It does not depend on the future, only all of them are depending on the, depending on the past values, but not the future. Input causes output. That's what that's causal. It depends on the past or future. Past or presence, not the future. Laplace transformation of x of t minus tau u of t minus tau, it will be x of s, then e power negative s of t. So we will say that e of power negative s over t, st or s tau, because here we have the time shifts, minus tau. Whenever we have minus shift, this will make this exponential, e power negative st, because of the phase shift. So x of s, because since this system is causal, x will be x of s. So how do we prove this? So Laplace transformation of x of t minus tau u of t minus tau. This is actually equal to the integral from 0 to the infinity x of t minus tau u of t minus tau d tau. And we can split this integral into two parts between 0 until t until tau x of t minus tau. Actually, that's u of t minus tau dt plus the integral between t to the infinity x of t minus tau u of t minus tau dt. And u of t minus tau is actually operated at t equal tau. Before than that, it will be 0. This yields to be this 0 and this equal to 1. So the output will be 0 plus the integral t until infinity x of t minus tau dt. Oh, I missed the exponential form. Exponential e power negative st. Negative st dt e power negative st dt. So your e power negative st dt. Okay, now how can we find this? Because since we have e power negative st dt, so what do we need to do? We can do some assumptions. Let's assume t0 equal t minus tau. Therefore, dt0 will equal to dt by making the derivative. Then we have t equal to t0 plus tau. And let's look at the terms. When t equal to t tau, this yields to t0 equal to what? So t0, t minus tau, tau minus tau will make it 0. When t equal to infinity, this yields to t0 equal infinity minus tau, any number minus infinity will be infinity. So what will happen? By changing the variables, it will be the integral between 0 to infinity x of t0 e power negative s tau plus t0 d t0. Then we can do the following: 0 to infinity x of t0 e power negative s tau e power negative s t0 dt0. This is constant, put it outside of the integral. By putting it outside of the integral, yields to be e power negative st, then the integral from 0 to infinity x of t0 e power negative st0 dt0. This is the definition of Laplace transformation, which is x of s. Therefore, the output will be e power negative s tau x of s. And that's it. This is the proof. You are not required to do the proof every time unless you've been asked. So, the overall, whenever you see any, I'm going to put here, any x of t minus tau, u of t minus tau, t minus tau will make a phase shift. This is exponential in direct shift because it's called the time shifts. So the exponential will be only whenever we have that time shifts. The exponential will not possible. Now let's go to another property, which is time scale. Scaling. So basically, we need to do the Laplace transformation of x of a t. It's not a function of time now, a of t. There's a constant. How to find this? So there will be a result about it, but now let's try to derive it. Then we will see. So it will be the integral from 0 to the infinity x of a t e power negative st dt. So the best thing is to do the integral using change of variables method. You should be you know this, we already applied this many times, but also you know this from calculus 2. Basically, you will assume, I'm going to assume tau equal at, therefore d tau equals to d a times dt. So in other words here, t equal tau over a, therefore, in other words, dt equal d tau over a. Okay? Then when we change the variables, it will be, let's look at the integral. So when at t equals 0, then tau will be 0 as well. At t equal infinity, then tau will equal to infinity. So let's change the variables. It will be the integral between 0 to infinity x of tau e power negative s t equal tau over a. So it will be tau over a d tau over a. Okay? That's the integral. So we will put 1 over a outside the integrals. 1 over a, the integral 0 to infinity x of tau e power negative s over a tau d tau. Okay, so how can we calculate this? Basically, by looking at this form, this is equivalent to x, but not x of s, it's x of s over a. Why x of s over a, not x of s? Because this variable, s over a in the middle. You can assume this as, for example, let me call it as s2, so it will be as the integral 0 to infinity x of tau e power negative s2 tau d tau. So this will be equivalent as x of s2, and now substitute s2 as s over a, so it will be as x of s over a. Then the final answer will be 1 over a times x of s over a. This is the proof. While you can use the overall expression when you convert this x of a of t, the overall conclusion. When we do Laplace transformation, it will be 1 over a x of s over a. That's the overall results. Okay? Now, I'm not sure if we have time. So we have 2 more minutes. I think let's stop here. the next lecture we will go more in properties of the process.